Okay, so I will resume the lecture on the tensor. Antoine. So yesterday I presented the tensor train decomposition and showed various properties, and namely the best approximation property, which in my mind is the right generalization to tensors of the SVD. So originally I wanted to present DMRG in the end, but since there were many questions about DMRG yesterday, I thought that it would be a good idea to do it today. But just before that, I think it's instructive to look at a small example, just to have an idea. Yeah, just to have an idea of what are the ranks that we can get from a simple example. So just the thing that I will be using. Maybe I just recall the tensor train decomposition. So if I have a tensor like this, if I write it this way, then yeah, I'll just recall. So this is valid for all mu's, and these matrices, they have this shape. And so one thing that we have seen yesterday is that the ranks, so the size of the matrices that appear in the tensor train decomposition, they are related to the rank of a particular reshape of this tensor. So namely this one. So here my tensor C, this belongs to R to the 2 to the L. And so this matrix here belongs to R to the 2K times 2L minus K. And also, yeah, so I won't write the estimate, but namely the best approximation is characterized by the singular values of this reshape. Okay. For all K. Okay. Change the chop. So let's see the small example. So the example that I'm going to take is the following. So so I'll consider two space orbitals. So phi A and phi B. So these are space orbitals. So namely, they are then some L2 functions of free, and I will assume that they are orthogonal and normalized. So you can think of phi A and phi B being the anti-bonding and the bonding over orbital of an H2 molecule, for example. And I will consider the states psi which is the Slater determinant of a linear combination of the two. So well, I add some spin. So it will be, yes. So it will be this one, up. Well, it doesn't really matter what I put here. So this will spin up, and then the other one will spin down. Okay. And now, so first thing is that I will, so I will choose, so now my computational basis is phi A up, phi B down, phi B up, phi A down, phi B down. And I will write the representation of psi in this basis. And first, I will choose an ordering for this basis. And for example, what I can choose is the canonical ordering, so the one that depends on the energy. So so here I'll use the canonical order of the orbital. So namely, I will, so I said B was bounding, so I will do it this way. So up, A down. Okay. So this is my, and I will write, yeah, so I will write psi. So now I expand everything. So if I expand everything, this, don't forget the spin. That's a prime. S prime, phi A up, phi B down. So now this one I get a minus sign. Because of the ordering. And I get a plus S prime. Okay. And now I will rewrite it in terms of occupation of the occupation number basis. So because I chose yeah, sorry. Yeah, I think it, yeah, okay, I mixed. Yeah, but what have I done? No, I think it's okay, yeah. No, it's okay. But yeah, no, it's this one should be at the end. Yeah. Just yeah, the second one I should switch, right? Yeah. Yeah, if I choose this, yeah, mixed, okay. Sorry, A and B, so I wanted to, okay. So this is right, then, yeah, so this gets a minus because I want to have this ordering. So it's this times this, okay, phi B down, phi A up, okay. And now it's this one with this one, and I get a plus. Yes, I wanted this to be the bonding. So this bonding. Yes. Yeah. I wanted to be smart, but it's kind of okay. So now, yeah. So now I choose so now I write it in terms of occupation numbers. So if you recall, now I parameterize these Slater determinants by looking at well, whether each orbital is occupied or not. So here, the first two orbitals are occupied. So I get ones and then zeros. Here, it's kind of similar. So the first is occupied, then the second is unoccupied, unoccupied, occupied, and so on. So here, this is phi 0, 0, 1, 1, and this one is phi 0, 1, 1, 0. Okay. And yes. Okay. I mean, okay. You can think of yeah. Okay, so if you have an H2 molecule, okay. So I mean, okay. In the minimal basis, you have if you diagonalize the R3 Hamiltonian, where H is well of the H2 molecule, then the first so the ground state is given by something which looks like this. So it kind of looks like just a superposition of the hydrogen ground state on each orbital. So this I call the bonding orbital, so phi b. And you have a kind of the flipping here, which is the first excited state, which looks like this. Yeah. And so this is the anti-bonding orbital by A. And yeah, well, and in terms of energies, yeah, so I think the classical diagram is that so this is the energy, so this is the energy of H, and then if you look at the energy of H2, yeah, so the anti-bond, so since it's a bonding orbital, the energy of yeah, like this way, so the energy is a little bit lower than the single hydrogen atom, and the other one is a bit larger. Something like that. Yeah, I'm not sure about this diagram. It's the way that I order the thing. So if here I just expand the, so this is this one. No, it's this one. Okay. So I need to. Okay. Okay. So now, yeah, I have my, so now my coefficient tensor, if I look at, so then, yeah, I've just, so, okay. In the occupation number representation, I just have 4 non-zero coefficients. So, no, so in the occupation number representation, or the Fock space representation, so I have C0, 0, 0, 1, 1, which is equal to C prime. I have this coefficient here. I have this coefficient here. And I have this one. Okay. And now, yeah, now I will look at so I want to determine what is the the bond dimension, so the maximal, well, the rank where it seems to be critical. So if you remember, it will be to well, associated to the largest possible matrix that I can have. So it will be in the middle. So I need to look at the reshape of this tensor when I kind of cut between these two indices. So this is what I'm going to write. So the reshape. So this will be my C mu1, mu2, mu3, mu4. So I have a 0, 0 index, 0, 1, 1, 0, 1, 1. The same goes here. So for the 0, 0, 1, 1, I get one component, which is this one. For the 0, 1, 1, 0, I get this one. For the 1, 0, 0, 1, I get this one. And finally, I get this. Okay. So as you can see, I mean, you have only non-zero coefficients when when you have exactly two mu's that are equal to 1. So this just reflects the fact that it's a two electron state. And so now, if you look at this matrix, and if you assume that these coefficients are non-zero, then you see that this matrix has rank 4. So you know that by this characterization, if I want to get an exact representation of this tensor, I need a rank 4 matrix for as R2. So R2 needs to be equal to 4. I mean, it's anti-diagonal. De toute façon, tu peux tout flip et puis. So this reshape as so C mu1. So the rank of this matrix is equal to 4. And so this means that the R2 is equal to 4, R2 being the TT rank of the exact representation. Okay. It's because of this characterization. So the RK here is characterized by this rank because of the TTSVD that we have seen yesterday. Okay, so now what is maybe a little bit more interesting is to see what happens if because here we have chosen this ordering for the one orbital basis, but we can also change the ordering, okay? So let's consider another ordering. And the other ordering is, yeah. So another ordering of the space of the orbitals. So this is this one that I will consider. So now I order them by spin. Here it doesn't really matter. Okay. So when I do this, I will get a different parametrization of the determinants. So so if I look at my state psi, I will get so this one. So now, yeah. So now I get. So now phi A up and phi A down. This is associated to this, so to the second and the last coefficient. Here, it will be higher. The sign changes also. Okay. Okay. No, the sign changes because you have. Okay. I wanted to do all in one step. I will do it in. Okay. I mean, so if you expand again the determinant, this is what you get. So up. What? Ah oui, parce que je changeais les. Ah oui, ok. En fait, j'ai pas les mêmes notations sur mes notes. Ouais, ok, ok. Je vais faire S. Oui, en fait, il faut le faire en regardant le truc là-bas. SC prime, hop. Phi B up, phi A down, ok. Ok. Si I think it's plus again. Yes. Okay. Now I think it's correct. And so now, yeah, now I changed the ordering. So the labeling of these determinants changes. So I get 1, 0, 1, 0. This one here is 0, 1, 1, 0. This one here, so I've put a tilde to just emphasize that's tied to another ordering. 0, 1, 0, 1. And here it's 0, 1. Ouais, je viens de me rendre compte, c'est 1, 0. 0, 1, ouais. Yes. Okay. So now you play, so now you have a different set of coefficients. So the coefficients become C10, 10, so it's this thing. C1001, it's this one. Okay, so now it's same game, you look at the reshape. So the reshape with respect to the first two against the last two. So again, the indices is 0, 0, 0, 1, 1, 0, 1, 1. Same goes here. And now, yeah, so 1, 0, 1, 0, I get SS prime. So I have SS prime here. 1, 0, 0, 1, SC prime. 0, 1, 0, 1, this one. And 0, 1, 1, 0, this one. Okay. And so now, yeah, there's so now another thing that you notice is that to go, well, you multiply C prime S prime by C in the first line, and well, in the second line of the matrix, and by S in the third line. So in fact, this matrix is of rank 1. So this coefficients matrix. Up. The rank of this is equal to 1. So this means that the exact representation of this tensor can be achieved with this R2 being equal to 1. So, this example is just to illustrate that so in general, the approximability of your state will depend on the ordering of your one electron basis, and I mean, to me, at least it's not clear at first why this ordering should be worse than this one. It's not at least for chemists, I guess it's more natural to use an energy labeled basis or an energy ordered basis than this one over there. Although for tensor trains, that's the one that you should use.
When you go on with the algorithm, you reshape again. So at the end, it's the same. You have tensors with from whatever the ordering, you have some relation for the one that you get for the tensors. I mean, for instance, the sum of the ranks of both tensors are the same.
I mean, no, here you have a different ordering and you have different ranks.
Yeah.
I mean, in practice, it will be the same thing. If you choose a wrong ordering, you will get, well, basically, if you choose a wrong ordering, because you cannot do infinite ranks, then you get a wrong energy, basically.
Only a simple case that the ordering is put all the spin and same spin on the box.
So there is no general rule. There is, however, a kind of a scheme which is called the Fiedler ordering that is based on the mutual information that will I will explain later in the lecture. Yes.
I have a last question. So you put as the condition that the fixed orbital are orthogonal. So if they are not orthogonal, can you use this formalism or adapt it?
I think then it's related to this basis. Yeah, I'm not sure it's really needed here when I parameterize the tensor, but I think it's I mean, it's like always, yeah, you do. Well, I mean, well, no, I never used that, but it's, yeah. Yeah, I think, yes. Maybe just like, what?
So I was wondering, so there is this change in the rank in each order, but we just looked at this kind of middle tensor, but there is the first one and the last one.
Yeah.
When you compare after the first or before the last. And I believe they are ranked 2. Is it true?
Yeah. In both cases, they would be ranked 2 in the, so R1 will be, yeah.
Like, you're giving some rank. I don't know how to call that.
No. I mean, you get, no. So in this case, okay. So maybe, okay, the brush is here. So if you do, so then you can, yeah. So basically, to get the other ranks, you just do the according reshapes. But for the canonical order, then the TT ranks are the following. So it will be R1 equal to 1, R2 equal to 2, sorry, R2 equal to 4, and R3 equal to 2. And for this spin ordering, let's call it this way. the TT ranks are this one. So what you gain is that here you would have an A2 of mu2, which would be of this size, whereas here you would get, yeah, call it tilde, which would be of this size. So you gained in memory, but you didn't lose any accuracy in the representation of the state. It's the exact representation of your state. Yes. Yes.
So this means that you have that your state is not correlated in a way because your wave function in a way is just a product of an alpha orbital by a beta orbital.
Yeah.
So therefore, it's not correlated.
Yeah, if you so these these orbitals are not correlated to these ones.
The answer that you put in the first place is not correlated.
Yeah, I mean, yes. I mean, because it's a, I mean, it reflects the fact that it's a tensor product between a spin up and spin down orbit. Yes. Yes, exactly. Yes, that's another way to say it. Yeah.
Like the two axes, like the determinants, like the potential one, then you have zero coefficients for symmetry reason. And therefore you just have the DB bar, I mean the FD down and the A up, A down coefficients.
Yeah, okay.
So that the matrix then that's what happens. Just with the prime and SS prime.
Yeah. I mean, here it's a very simple. Yeah, I'm not saying that this is the ground state of the H2 molecule. I'm not saying. No. It's here. It's still a Slater determinant, but of a linear combination of space orbitals. Yes. Yeah, I mean, it's just to kind of. No. I mean, yeah, but also I've started with a very particular state. I mean, that's for. So this example is designed for this state. Yeah. I mean, okay. So maybe just as an additional note, I mean, this example is just yeah, it's a fancy rewrite of a Bell state, okay, in a quantum chemistry case. So usually, I mean, the usual example is the example of a Bell state, but yeah, here I gave it a little bit of an electronic flavor. Ouais, oui. Je peux le réécrire comme les étapes. Parce que c'est. OK. No, but with a specific choice of C and S and so on. Yeah. I think so. I had the question.
Choice of the coefficient 0 and 1 in the matrices that you draw, like the reshaping is not the same if you choose to say that the first line is 0, 0, then the second line is 1, 0, the third will be 0, 1, and the last 1, 1.
Yes.
So it changes it doesn't change the rank, but it changes the matrix, and therefore it changes the SPP of the layers.
No, it does. So what it changes, it doesn't change the singular values. That's the important point. So because the approximation result is so the approximability is related to the single values, not the SVD in itself. Yes, and that's related to the fact that these are not uniquely determined. You need yes. If this no, they can change in the orthogonal matrices. So here, if you, I mean, if you swap these two, you get an equivalent matrix, which will have well, not equivalent, but yeah, I don't know. Yes, and yeah, so the singular values will be the same, but the SVD representation, so yeah.
You will not change the vectors, you will not rotate them together, just swap the order.
Yeah.
So the fact that you got the rank equal 1 here, is it the signature that your original wave function can be written as a Slater determinant?
Yeah, Slater determinant of spin up and spin down. Yeah. Yes.
So that's the reason. Because
yeah.
If I look at the second position, when you look at that, it's a multi-determinant wave function.
Yes.
So from that point of view, you could say, oh, there's correlation, but there is no correlation in quantum chemical meaning.
Yeah.
Because you can rewrite it as a Slater.
Yes.
So this construction is connected to this.
Mm-hmm. Yep. Exactly. Yeah. Well, usually you don't, but there is a scheme that I will explain that later in the yeah. But yeah, it's a tricky question.
To ask about the count of the number of key parameters. So if I take this initial parameterization, I have only 4 parameters, right?
Yes.
Now, if I go to, for example, the speed of ordering, I have many more, because in A2, I have 2 parameters for fixed mu2, but then there are 2 values of mu2, so it's 4.
Yeah.
And then you have A1 and A2, so that's 12.
Yeah.
So, and for the canonical order, it's even more.
Yeah.
So it's really a random parameterization that you have.
Yeah. So it's related to the fact that first, I mean, the state is not really high dimensional, and second is because we work in the Fock space representation. So in the Fock space representation, you have in fact 2 to the power of 4 coefficients, because here you have 4 orbital bases. So the underlying dimension is in fact 16. But yeah, I mean, here you already know that it's a 2-particle state, so you have only 4 coefficients that should be non-zero. Okay. So DMRG. DMRG. I believe it's free DMRG. So yeah, just think I never said what DMRG stands for. So DMRG stands for density matrix renormalization group. So as I said, it comes from, well, so it was first, yeah. So the creator is Stephen White in a paper in '92, and then for quantum chemistry, it was in '99, still by White. And so DMRG is really so it's really the algorithm that solves the Schrödinger so the Schrödinger equation using tensor trains. So maybe I should write that. So DMRG is so it's the algorithm to solve the many-body Schrödinger equation. With tensor trains. So yeah, I think I will do. So first, yeah, the first thing that we need to see before the algorithm is first. So at the B, so yeah. So previously we have seen how to write a state as a tensor train. Now what we are going to see is how to write the operator in as something that is suitable for tensor trains, and then we'll see the algorithm. No. Okay, maybe okay. So I'm not fully sure that I have the right explanation, but I think it's clearer when you see the algorithm. So maybe we'll come back to that at the algorithm. Okay. So yeah, we'll see how to write operators that is suitable for the use of states represented by tensor trains, and this yeah will be called. So I mean, usually it's called matrix product operators. So this is MPO, and yeah, I mean, I'm not sure it's a standard way of calling them, but I call them tensor train operators, so TTO. Okay. So yeah, I will come back to the graphical representation of a tensor train. Maybe so if you remember, yeah, maybe I will write so the TT decomposition was like this. Okay, so each of the A's that are appearing, so the first one is the row vector, the last one is a column vector, and then everything in the middle is a matrix. And so you had the graphical representation of this thing. So you had the tensor C, which was a node with the 3 edges, which you could write as a first a first node representing this tensor here. Since you have yeah an index over which you sum with the next one, you have a connected edge to the second tensor, which has a free edge, and so on and so forth, until the last one, which has just one sum with the previous tensor and the last one here. So yeah, so again, a free edge means that you have an index that you can choose. A shared edge is an index over which you sum. Okay, over the shared index. Okay. So now the operator. So the operator H, which act on the state, you can see it as a big matrix. So of size 2 to the L, 2 to the L. And so if you write kind of the graphical representation, yeah. So this will be my H. So yeah, plain nodes will represent states, and just circles will represent operators. That's my convention. So yeah, so my matrix here, it has a lot of indices. And so if you try to represent it as in its graphical representation, I mean, it has many legs that pops out. Okay. And now, typically, what you would like to do is, for example, a matrix vector multiplication between H and state. Okay. So this in the graphical representation, and so remember we will start with something which looks like a tensor train. So in the graphical representation, C will be given by this. Okay. Yeah, maybe I should write it this way. And I sum over the shared edge, which should be this one then. So if I represent my matrix vector product, it should look like this, kind of. So here. Okay. And by looking at this drawing, the thing is, so you realize that yeah, I mean, so if you try to, so if you have to do that for every index, well, for all the indices mu, and you have to sum over all the news here. So here, this would be mu1, mu2, and so on. Well, you realize that it's a heavy computation. So so the idea would have to have an operator which kind of reflects this structure. So what you would have, in fact, well, what you would like to have, in fact, is an operator which is kind of a product of the indices mu1, mu1 times something which depends only on mu2, mu2, and so on and so forth, just to be able to kind of decompose index by index this matrix vector product. So this is the idea of the MPO or TTO. So TTO, MPO. So the idea is to write kind of an equivalent of the tensor train decompositions for the tensor, where you gather the mu1, u1 index, mu2, mu2 index, and so on and so forth. So the idea is to write H. So maybe I will write first in its diagrammatic form. So you want to write something which looks like this. Okay. So I have and now if you look at the matrix vector product, in this case, now if you look at the matrix vector product, it looks much nicer because now, yeah, maybe I will go and do the case A equals 4 just to have a complete picture. So this will be my A1, 2, A3, A4. Up. This will be H1, H2, 3, 4. And this looks nicer. As you see, you could do these sums. I mean, okay, it's not the most efficient way to do it, but you can see that you can kind of do these sums in a more structured way. And you would, yeah, it would scale much better than keeping the whole operator in its original form. So that's the idea of using this operator, and maybe to yeah. So maybe I should label some stuff over here, and so maybe to just expand this formula. What you then would write is so then the formula that you have is the following. And then for all mu k, then everything is a matrix except the first and the last one. Which are row and column vectors. Okay. Okay. So now one question could be, yeah, how do you achieve such a decomposition if I am given some operator in this format? So the full operator. The thing is, this is what? So if you merge these three indices, so the mu1, mu1, mu2, well, the mu1, mu1 together, the mu2, mu2 together. Okay, so maybe if you flip this edge over this side and this edge over this side, and you gather them, well, you realize that this is nothing but the tensor train decomposition of just a tensor where you gather some of the indices. So theoretically, you could get this decomposition by doing a tensor train decomposition of this operator. So yeah, that's something that I will write. So the TTO decomposition. So it's exactly of of the tensor where you gather mu1, mu1, mu2, mu2, and so on and so forth until mu L, mu L. And this tensor is of size 4 to the power L. Okay, so far so good. All right. So now, before looking at what happens to the electronic Schrödinger operator, let's look at some of the algebraic properties of tensor train and or should I do? Yeah, okay. Well, I'll do it as originally planned. Okay, so I will speak about algebraic properties. So for example, if you are given two operators in the TTO format and you sum them, are you able to write a TTO format just using the TTO that you are given? And same thing for the product. So algebraic properties. So the sum of TTO. So let's say that I have so the thing is, until now I kind of refrained to do that, but I find it quite handy to use kind of the same letter for everyone. I hope you wouldn't be too confused. So so the tensor train operator decomposition of my operator, they are all called H. So that's kind of a convention that I will use. So let's say that I have this, which is given like this. Where these ones, they have these ranks. Same here. That's a G. And up. So this has sides. Okay. So now, if I want the sum, then this has a TTO decomposition, which can be written like this. So basically, the TTO decomposition, well, one TTO decomposition here. So the TTO decomposition, I write it kind of schematically like this. Yeah, I don't have so much space. So this, I mean, okay, I shouldn't. Yeah. So basically, what you do is just you write the block diagonal. So you write it as block diagonal matrices. So except for the first one, so this is for k from 2 to L minus 1. For the first one, so it's a row vector. So you just get so you collect it just in a row vector. And for the last one, okay, I don't have any space. And so for the last one, you collect everything in this vector. Okay. And so since you write it in a block diagonal form, you see that all the H, they will just hit the next H, and the G's, well, same thing goes for the G's, okay? And so here I just have zeros. And so if I look at the size, then the size here, it will be R1H plus R1G. And here, yeah. So I get a representation which is a sum of the ranks. So here, representation is the sum of the ranks. So the thing is, I mean, as you can see or guess, I mean, this won't be optimal. So imagine that you sum a lot of operators of this form. You can imagine that yeah, I mean, this representation is not optimal. So you would have to well, there is a way to find another representation, another smart representation of this. And for example, if you just take the case G equals to H, I mean, then the sum would be twice. Yeah, it would be 2H, and then the factor 2, you can just move it in one of the tensors here. So this representation is not optimal. It's just one possible representation of the sum. So now let's look at the product. The products, yeah. So for the product, I think it's better to do it. So I will look at the product GH. And I think it's better to use the, so yeah, you can do the algebra, but the algebra is kind of cumbersome. I mean, as always for tensors. So I think the best way is to do it by using this graphical representation. So here I will fix L equals to 4. Okay. So this will be my new. This will be my G. Okay. So in the graphical representation, 1, 2, 3, 4. So in the graphical representation, I just sum over the shared index here, 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 and here. So this is the graphical representation of my matrix product. And now I want to get from this representation the tensor, the TTO representation, which kind of looks like this. And so, yeah, if you want to have this TTO representation, what you can, well, I mean, what you can kind of see is that you would get something similar to this if you merge these two in the same tensor. Okay, so you would kind of merge here, 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 here. Okay. And so now, what is and so then these two indices here, you would merge them in one single index, so one single edge, to get this picture. So now, what is the formula that is giving this tensor? So I have an H1, and I sum over a shared index that I will call a mu tilde. Okay. I have a tensor G1, and I sum over the shared index mu1 tilde. And here I have, I have, yeah, okay. Maybe I should have said that. So so a little bit of vocabulary. The index that, well, the index here, they are called, so the free ones. that you can choose. These are usually called the physical index. And the ones that you sum over, usually they are called the virtual index. So here, yeah, you have a virtual index which is particular to H, and you have a virtual index that is associated to G. So yeah, yes, I mean, yeah, I don't know. Yeah, let's call it alpha 1G, and you have an alpha 1H if you want. And so if you kind of write it and you sum over mu1 tilde, okay. And so if you want to write it in a more matrix form, I mean, this is exactly the sum over mu1 tilde. So here it's from 1 to 2, G1, mu1, mu1 tilde. And since you have an index for each one, it's just a Kronecker product with the other tensor. And so yeah, I mean, here you could see the size of this tensor was R1 times, I mean, the product of the dimensions, and here it's the same thing. So it's 1 times the product of the dimension. And so yeah, this is basically the formula. So the formula of the product, yeah, I can write it here. I put the space. So a TTO decomposition will be just the sum of mu k tilde of gk mu k tilde tensor product hk mu k tilde mu k. And so this is of size then R k minus 1g k minus 1gh times rk g rk. All right. So yeah. So basically we have, and again, I mean, same thing goes for the product here. For the product, I mean, this won't be usually this won't be the optimal representation in terms of the dimension of the matrices of your product, but I mean, you can start from here and then apply some kind of compression scheme to reduce the ranks. That's kind of the idea here. But you 1 to 2, 0 to 1, yeah. Yeah, sorry. Julia indices. Yeah. 0 to 1. Okay. Okay, so now let's go to the electronic operator. Yes, you can, but people don't really do that in practice. I don't really know why. But yeah, you could. So basically, because you have all the operations, and then the only thing that you need to have is kind of a good compression scheme. But I think that's kind of the tricky thing. Okay, so electronic Hamiltonian. So the electronic Hamiltonian in the Fock space representation is written as the sum of one body and two body apart. And so what we want to do is kind of see if we can apply these rules to build an MPO representation of the operator. And so what we need to look at is at these creation and annihilation operators. So now creation and annihilation as TTOs. So yeah, so if you write these operators as matrices that are acting in the tensor space, so the R to the 2L, so as matrices acting on what you have is that so the annihilation operator it will act only on the orbital I, okay? And for all the other orbitals, so I mean, okay, since they are fermions for all the first orbitals, it will just act. So it will just flip the sign if it's occupied or not. So here it's this 0, 1 labeling. So if it's occupied, it will flip the sign. So you have this representation. And then for the site I, it will destroy if it's occupied. So if I don't mess up, it should look like this. Yes. Yeah, I will need some space. And then for all the others, it will do nothing. So it will be just the identity. Identity. So here it's really for okay. Same thing for the creation and operator. So it's just the same thing. Yeah, let's flip here, of course. And then it's identity. Okay. And so here, what you can see is that the creation and annihilation operators, they have this tensor structure. So in the sense that this matrix, it only acts on the indices mu1 and u1. Okay. The second one, it will only act on the index mu2 and u2. So it's already, in fact, a tensor train decomposition of the TTO decomposition of AI and AI dagger. And the rank, since it's a tensor product, it's just a TTO decomposition of rank 1. So this is so here we have a tensor, so a tensorized. Yeah, we have a tensor product. representation. And so this is, so this means that AI and AI dagger, they have a TTO representation of rank 1. And so now, if you look at the algebraic rules, it means that for the two body and the one body operators, you have also rank 1 TTO representation of this and this. And so now, if you apply the sum, the algebraic sum rule, since you have at most L4 terms in your operator, you have an L4 representation of your TTO. So I'm going to write it down. So might be algebraic properties have a TTO representation of H of rank, which case as L to the 4. So this format preserves the sparsity that you have in the Fock space representation of your electronic Hamiltonian. So yeah, that's nice. So the thing is, in fact, so to just tell you so this is in fact not optimal. You can reduce it to L square. So this is related to the fact that since it's a two-body interaction, if you do if you split the system in two, so which is what you do when you do an SVD, you have either L square interaction on one side, L square interaction on the other side. So it means that you have at most L square, you have at most L square singular values that are non-zero. And if it's unbalanced, so you have L and L cube on one side and the other side, then it means that it's a rank L, it's a rank L reshape. So this is kind of, the motivation, what's its L square. And so in fact, you have an big O of L square TTO, exact TTO representation. Which is, of course, much better. So you can actually, start from this Hamiltonian and write the L square representation. But then, so, and this is also assuming that you have you have no, you suppose that you have general one body and two body interactions. So in the sense that you don't assume anything on the H and V except that there are one electron and two body electrons. Two electron integrals. So for example, if in statistical physics, I mean, most of these V's, they are zero, so this would be even smaller in the end. Yes. No, you have more because it's a matrix. It's you have. Yes, that's kind of that. Yeah, you have L square matrix. Yeah. No, it's not less. No, it's less if you have additional terms that are zero. That's what I say. here you don't assume anything on V and H. If you assume, for example, that most of them are 0, then you can even compress even more. All right. So 10 minutes. Yes, that's tricky. Yeah, but the coffee break is ready. Yeah, because if I start the MRG, I guess it doesn't make so much sense. That's yeah. I guess it's a good yeah. Good. It's because yeah, I mean you do the splitting of this term, and then so if you do a splitting of this term of these coefficients, so either so in a left and right part, so either I don't know, you have ij in this and KL in there. So if you do the reshape, then it will be an L square times L square matrix. And otherwise, if it's something like this, then it's L times L cube. And so this is of rank L. So I mean, and so if you do all the cases, then the optimal rank should be of order L square, and not this number of terms. Okay, so I think we can have an early break.
Maintenant, tu veux faire l'opérateur de comptage à quoi AI?
Ouais.
Cette matrice avec cette matrice,
Ouais.
Et donc,